Okay, we are live, and I have the pleasure to introduce our last speaker of the workshop. This is Ribhu, Kaul of Kentucky, and Ribhu, at your leisure, please, you take it away.
Yeah, thank you so much. Thanks for organizing this, Tim, and all the other organizers. I really appreciate it, and I can't imagine how much of a hassle this has been for you guys to put together. But I really appreciate the chance to talk here, and I'm sure all of you are tired of watching online talks, so I'll try to be as quick as possible. Okay, so I want to tell you a little bit about some work that I've been involved in recently. Before I do that, I wanted to just advertise this workshop that we're organizing, which I think will be of interest to many of you next year, and we really hope it'll be in person. It's at in Florence at the GGI, and it involves some people in high energy physics and condensed matter. And so I think this, I hope many of you will apply and join us at that workshop to really enjoy it. So it's between October and November in 2022. And so if it looks like something that's of interest to you, I hope that you'll mark your calendars for that. Okay, so, and so if you look up the schedule at the GGI, you'll find it listed. Okay, so let me move on and tell you a little bit about the kinds of things that I'm interested in, which, I'm sure is very familiar to many of you. So, I always thought that quantum field theory meant that something had to be in the continuum. And, I was Google searching and I found out that there's this idea of a lattice quantum field theory, which I like a lot because it's related to things I understand. And so I'm not totally sure that I understand the meaning of that word, but my understanding is it includes models which we would just call many-body lattice models. Okay, so like the kinds of models that we're often interested in condensed matter are constructed out of fermions, like this model up here, which is the Hubbard model. Let me see if I can get. So yeah, so like the Hubbard model over here, which is defined in terms of lattice fermions, which anti-commute at large distances, and then there's the famous Ising model of spins. So spins and bosons are really the same thing because the operators that sort of act on the Hilbert space commute at when they're far away from each other. Okay, and so in condensed matter, often our inspiration to write down these models comes from some experimental system, and something which is not related to experiment, and sometimes it's very close to experiment, and experiment sometimes is complicates things because it doesn't do things like the way you want them to, but it turns out sometimes these complications lead to new richness and subtlety and interesting ideas. And so I'll talk a little bit about that as well. So I'm going to show you some experimental data, okay, believe it or not. All right. Okay, so I have roughly 2 parts of this talk, and again, I expect it won't go on for 2 hours, but if you guys have questions, it could. And so the first part, I want to tell you about some work which we haven't published yet. It's almost ready. It's going to come on the archive maybe next week, and it's about criticality in fermionic systems. Okay, and so I begin first of all by acknowledging my collaborators, especially Hanqing and Emily, who are really fantastic young scientists. It's funny, I used to always think of myself as young, but now I guess after collaborating with Hanqing and Emily, I'm realizing that I'm getting old. And Shailesh and I are really lucky to have these collaborators, and I'm going to show you basically what they did. I mean, we were just pretty much sitting on the side and watching this happen. Okay, confusingly, we are also called UK, the University of Kentucky. I think in Kentucky, the only foreign country we know of is Tennessee. And so we didn't, when they made this acronym, I think they didn't maybe know about where this conference was being held. Okay, so all right, so the experimental system, which has been a huge motivation in condensed matter in the last the last 20 years, has been graphene. So, I'm sure Farquhar mentioned this. Unfortunately, I missed his talk because it was in the middle of the night. But if you take a hopping model, and we can get into chemistry of why this is the right hopping model for carbon atoms on this lattice, but maybe I'll avoid that. I'll talk a little bit about chemistry later. Roughly speaking, you can think of each carbon site as consisting of a spin up and spin down site, and then electrons hop there. Okay, so this is a partial model of some orbitals of carbon that turn out to be chemically relevant for graphene. So if you've solved this problem, which I'm sure that all of you have done, you know that you get this dispersion, which when you look at very low energies, has this relativistic linear form. Okay, this has been very, so graphene is exciting for many reasons, and the electronic dispersion is definitely one of the biggest ones. But there's a lot of other reasons why people are interested in graphene in material science and condensed matter. But one of the things that has been sort of difficult in graphene, and this is something that came up in Sohn's talk, is that when electrons interact typically in these materials, they're very weak. Okay, and the heuristic picture, again, as Sohn said, this is not quite extremely well understood, is that the bandwidth of these electrons are very large. Okay, so they're typically of the order of electron volts, and so interactions are very weak compared to the bandwidth, and so to a very good approximation, electrons in graphene don't interact. Okay, so an interesting question is, what experiments do we know in graphene which actually show that electrons interact? And the only exception for a long time was the fractional quantum Hall effect. Okay, it turns out there's also an integer quantum Hall effect that requires interactions in graphene. But the thing which, for people who are not in this field, was pretty much, was basically a revolution in the last few years, was this, it happened in 2018, and there's already a Wolf Prize been awarded for this discovery.
Sorry,
yeah.
That's the question.
Yeah.
Just going back, so can you tell me what fractional Hall states have been seen in graphene?
Oh, what fractions? Well, I'm pretty sure. But there have definitely been quite a few fractional quantum Hall effect states.
Oh, you completely froze just as you were saying the important bit. Can you say?
Oh, no. Well, maybe my internet reflexively froze because actually I was saying that I don't actually know off the top of my head which fractions have been observed.
I see. There's something. I can't remember the story. There's something. Maybe this is what you're saying about the integer quantum Hall states. There's some spin splitting or something.
Yeah. So the interesting thing is, maybe this is what you're referring to, is that again, when you look at the dispersion of graphene in condensed matter, we call these valleys. So there are two valleys. So if you look at this, there's a Dirac equation at k and at k prime. We call it. So if you let me see if I can get this to work. So if you look at the Brillouin zone of graphene, it's usually drawn like this. There's a Dirac node at k and there's a Dirac node at k prime. And so in this linear continuum approximation, there's like a Dirac equation here and a Dirac equation here. And when you apply a magnetic field, so in this continuum model, these two valleys are completely independent. So in addition to spin, they become another label, which is often in condensed matter called the Valley quantum number. And so when you apply a magnetic field, you get a set of Landau levels which are associated with this part of the dispersion and with this part of the dispersion. And so when you fill these up to, so even in the regular quantum Hall effect, technically the integer quantum Hall effect, there are some integers in which interactions are important because otherwise this system would be spin degenerate. And there's this old phenomenon, it's called quantum Hall ferromagnetism, where the system sort of spin polarizes, and then so already that phenomena actually requires interactions. Now it turns out that, of course, in the real old experiments, you apply a magnetic field, so you break spin symmetry, and so you already favor one of those particular spin directions, even in an integer quantum Hall state. But here, because the magnetic field doesn't break the valley degeneracy, at least as far as if the crystal is perfect, exists even in a magnetic field. And so so the interactions have to spontaneously break the symmetry. And so there's some interesting physics that goes along with that, even in the integer quantum Hall effect in graphene.
See, thank you. That's really useful.
Can I also ask a question?
Yeah, yeah.
Could you try to give me an intuition why should the interactions ever not be important? I would think that that any, if they're long range, sufficiently long range, that they would always be important.
Yeah, I mean, this is a good question, and things that we don't, I don't know, maybe somebody understands, but it's sort of a difficult problem. But I mean, one point of view, which is maybe the condensed matter point of view, is phenomenologically, this is what happens. Or this is one condensed matter point of view. I'm sure many people have different points of view. That, phenomenologically, if you study these systems, they're mainly non-interacting. And so this is like the justification of Landau's Fermi liquid theory, is it's sort of a phenomenological theory, which is sort of self-consistently describes what happens. And maybe that's the best answer I can give you. I know that, as Son maybe also mentioned, there's some diagrammatic ways of studying this and justifying Landau Fermi liquid theory, but I'm not very familiar with them.
Could one somehow formulate it in terms of effective theory and just where you see that any interactions are irrelevant in some RG fluid?
Yeah, so at least in this linear dispersion case, the nice thing is that if you just consider 4 fermion interactions at tree level, they're irrelevant.
Sure, but these are not long range, right? In some sense, right?
Say it again.
They're not long ranged.
They're not long range, right? So I think Coulomb interactions are known to be marginal, and maybe one loop calculations show they're marginally irrelevant. So they actually do affect some logarithmic corrections to properties that people measure in graphene.
Okay, just like in 4D in principle. I was wondering whether, but so they're marginally relevant still, even when restricted. Okay.
Yeah. That's, I mean, maybe Farker or somebody else might know more about it, but that's okay. So anyway, so there was this big development, which I think is very exciting and something I'm thinking a lot about. So people realize that when you take graphene sheets, remember graphene is isolated from graphite, which has many sheets of graphene, and so naturally you have systems which form bilayers, and sometimes these bilayers, there's something called Bernal stacking, which is the standard way, commensurate structure in which graphene stacks, and I can draw it for you. But what happens very often, and in the last 20 years, people have reached the level of technology where this can really be controlled, is that you can twist 2 sheets of graphene with respect to each other. Okay, so here's a picture of these two. It's just a drawing of 2 honeycomb lattices which are twisted with respect to each other. And if you look, you can see, I don't know if you can see it on this resolution, but there's like a super lattice that forms inside this sort of combined structure. Okay. And the phenomenon of the superlattice is very familiar. It's something you learn in high school. Is that if you, here's a little Mathematica snippet I made. If you add 2 sine waves which have slightly different frequencies, there's an emergent length scale. Okay, so as the frequencies get smaller, closer and closer to each other, this length scale gets larger and larger. And even though, technically there's no periodicity in the sum of sine x and, okay, maybe not sine 1.1, but if I just took some random, irrational number, there's no periodicity in this sum of functions, but there's this emergent periodicity that appears if you ignore these fast oscillations. Okay, so this phenomenon is called beats, and you experience it when you hear 2 frequencies which are very close to each other. So now the interesting thing is, in 2-dimension, you don't have to have 2 frequencies which are slightly different. They can be exactly the same frequency, but now you can rotate the crystals with respect to each other. And this rotated system now shows this emergent length scale, which this is the huge periodicity, and there are tons and tons of atoms inside this each unit cell. So why is this interesting? So this was observed in experiment, and people knew about it, but then in this twisted system, and so it turns out that there are certain special angles, just like when you sum sine waves, there are certain special wavelengths at which the structure is commensurate, but in general it can be incommensurate. And about 10 years ago, people realized that there's a good approximation in which you can actually solve the band structure. Okay? And so what happens then is that you have these two Brillouin zones of graphene. And they have their Dirac nodes, which are slightly twisted with respect to each other. But then when the electrons can tunnel between these two graphene sheets, this band structure completely reconstructs. And it turns out that in this reconstructed band structure, and let me show you a picture. So actually the original idea was due to Castronetto's group, but then Bistritza and McDonald really studied this idea thoroughly. And they showed as a function of this twist angle, you can get very flat bands. Okay, so what can happen now is that the interaction scale, which presumably is fixed in this process, can get much larger than the bandwidth. Okay, and this is so this was a theoretical idea that maybe not many people took very seriously. But then this group of Herrero at MIT in 2018 actually constructed a device in which this happened, and they discovered superconductivity, ferromagnetism, anomalous quantum Hall. And now it's a huge thing. It's been repeated by many, many people. And the Wolf Prize from 2020 was given to Bistritza, McDonald, and Herrero in recognition of the fact that this is a major game changer in our thinking. And so the reason I bring this up, because it's not totally related to this conference, is that I think thinking about these systems could be paths to new quantum field theories, which we don't normally think about. Okay? Because these bands that you write down, they don't have simple tight binding dispersions like the way you think about in graphene. And I wasn't able to attend Farker's talk, but my understanding is that he must have spoken at least a little bit about this Gross-Novo transition. Now, this is something that we've talked about a lot, and I think even various people are interested in mass generation of fermions, but it's something that's never been observed in experiment. And it's part of the problem is that interactions are very weak with respect to bandwidth. And so you always just end up in this non-interacting semi-metallic phase. And so this whole system opens up the possibility that we might be able to realize this in nature. And I think that's very exciting. And that's motivation for studying these kind of field theories. Okay, now, as usual, experiment is always more complicated than what we imagine as theorists. And it's also exciting because I think we might be pushed to studying new kinds of field theories if you want to study interactions in such systems. Okay, so that's all by way of motivation. And now I'm going to just go back and tell you something pretty pedestrian that we did. I wish it was, we were working on this. I wish that we had some way of realizing this in graphene, but we're not there yet. Okay, so, we have tight binding models. Like the one in graphene, where you have a honeycomb lattice and you have electrons hopping, and they have spin up and spin down. So now you can ask, what are the symmetries of the system? So, they're the usual symmetries like translational symmetry, rotational symmetry, time reversal, but there are also these important internal symmetries. So the one, so if I take this Cj sigma operator and I multiply it by an SU2 matrix, that leaves this Hamiltonian variant because dagger, will transpose that matrix, and then of course it's a unitary matrix, so it goes away. And so this is a symmetry of the Hamiltonian, and this is the operator that sort of generates rotations of SU2. Okay, now it turns out that there's another symmetry which some people know, it's an SU2 charge symmetry. Okay, so it's not totally obvious in this representation. But roughly speaking, the idea physically is that, if you think of the Hilbert space of a single site, there's the empty site, there's a doubly occupied site, and then there's these two singly occupied sites. And so what the SU2 of spin does is it does an SU2 rotation amongst these two guys, but it doesn't act on the empty and doubly occupied site. Okay, but you could define another SU2 which acts in the space of the empty site and the doubly occupied site. That's independent, and as far as each other is concerned, they're singlets. So if I do an SU2 rotation, the spin, the charge doesn't rotate, but if I do an SU2 in the charge, the spin doesn't rotate. Okay, so there are these two SU2 symmetries, and this was discovered by, I think, C.N. Yang and Shuchen Chang maybe 15, 20, 30 years ago. Okay, so there's another important symmetry, which is it's a Z2 symmetry, which is the interchange of these two symmetries. Okay, so if you want to implement it in the Hamiltonian language, so this zeta I is a sublattice sign. So I'm imagining I have a bipartite lattice like the honeycomb lattice, and zeta I is plus and minus 1 on the A and B sublattice. Okay, so The Z2 transformation, what it does is if I apply this F operator on S, it'll become C. And if I apply it on C, it'll become S, sorry. And it's a property of the Hamiltonian. It's a symmetry of the Hamiltonian, okay, because it's basically a particle hole transformation on one spin layer. So remember, you can do particle hole transformation on both spin layers, or you can do them on one spin layer. And those are independent symmetries. Okay, so all these symmetries are very manifest if you write down the system in terms of Majorana fermions, right? So if you take every fermion on the A sublattice and B sublattice and write it as, you know, an A over here goes from 1 to 4, right? So what you can do is for the spin up electrons and spin down electrons, you can write them as two separate Majorana fermions, and then you get the Hamiltonian in this form. And now the symmetry has the fact that this Hamiltonian has an O4 symmetry is very apparent because the Majorana fermion transforms in the vector representation of O4. Again, as is well known, if you combine SU2, SU2, and Z2, you get O4. And so, you know, that's this Majorana thing makes it explicit, but this is maybe the physical way of thinking about what that symmetry is. Okay, so this is all these symmetries are present in any bipartite hopping model in any dimension. Okay, I'm going to be interested in two spatial dimensions, 2 plus 1. So now what people usually do is they take this Hamiltonian and they add a repulsion to it. Okay, and the classic way is with the Hubbard model. So let's ask how the Hubbard model looks in terms of the spin and charge operators. So it turns out you can write the Hubbard model basically as SI.SI minus CI.CI. Okay, so the Hubbard interaction is invariant under SU2 rotations of spin. It's also invariant under SU2 rotations of charge. Okay, but when you flip spin and charge, it actually is odd. So because S and C get into flip symmetry. So basically this.
You broke off for a bit.
Oh, I'm sorry. So
it keeps happening every once in a while. Do you have any signal on your end that the connection is weak?
It could be. And unfortunately, there may not be much I can do about that. I can put my video off.
Maybe
probably the talk would look better. So why don't I try and do that? And now, hopefully, I won't be, because I'm actually connecting with both these computers because of I'm using one as a camera. Is that better?
Well, let's see. I mean, most of the time it's great, and then your voice disappears and you freeze for a couple of seconds.
Okay, let's try it without the video and see how it works. So so basically there's the Z2 flip symmetry, and the Hubbard interaction is odd under this symmetry. Okay, so if I act by the symmetry, U changes sign. And so U is exactly, you know, it's like the Ising magnetic field. Like you can apply an Ising magnetic field on the Ising model, and U acts like an Ising field. So it breaks the Z2 symmetry and it's odd under the Z2 symmetry. Okay, so basically our question was that, you know, people usually study the, destruction or the opening of mass generation in Dirac fermions in the Hubbard model. And the Hubbard model breaks the symmetry. So an interesting question is, what would happen if you sort of added an interaction that preserved the symmetry? First of all, is it possible to preserve the symmetry in an interacting model on the lattice? Okay, so the symmetry is a property of the free system, and the simplest Hubbard model that you add breaks the symmetry. So first of all, is it possible to preserve the symmetry on the lattice? And if you can, you know, what's the kind of fixed point you get, and what's the kind of massive phase you get? Is it different from the usual? Okay, and the answer is yes to all those questions, and that's what I'm going to tell you about. Okay, so this is our paper. Again, Emily and Hanching are really the heroes of the story. I'm happy to present it on their behalf. So Hanching did lots of the renormalization group calculations, and Emily did developed lots of the Monte Carlo methods, and I made the PowerPoint presentation. Okay, so so idea is that we want a model which on the lattice preserves this spin charge flip symmetry. Okay, and so here's a very simple way to do it, and this may look a little awkward, but it turns out that this is very helpful. And again, Emily and Shailesh have developed some very sophisticated algorithms to simulate these models. And it turns out that this form is very convenient for that algorithm, and I'll explain the algorithm just briefly to you. Okay, so the idea is that you take the hopping thing, this operator, which you know has the full O4 symmetry, it has SU2 spin, it has SU2 charge, it also has a Z2 spin flip. And all you do is you can construct any function of it. And that function obviously has the full symmetry. Okay, so the function that we construct is just the exponent. Now you could also, if you, so let me explain this and I can tell you some alternative things you could do. Okay, so consider this model. It's a sum over bonds of the exponential of some number, which I'll talk about, times this hopping operator on that bond. Okay, so this term, now when you expand this exponent, it has, now because of fermions, this exponent doesn't have infinitely many terms. It truncates after some time because C squared is 0. But it has terms of order 2, of 4, of 6, of 8. And so, normally when you in condensed matter, you think you don't go past the 4th order operator. But as far as we're concerned, we want to study universal properties of some critical point. And so we don't really care about this. Okay? This is just it gives us a numerically tractable model. Okay. I mean, you could argue that people truncate models often to 4th order to give it an analytically tractable model. And since we're not worried about analytical tractability, we're just going to go on and use this term. Okay, so now this model is completely local. Okay, because it's sum of interactions on bonds, so it's completely local. It has the full symmetry, and so it's as good as any other model. And in fact, so there's been some mess up over here in the format here, but Anders Sandvik, my collaborator, and Roger Malko and I, and this is a review article we wrote, and we call these designer models, okay, because they're sort of designed to be de-signed. Okay, so they don't have a sign problem, and so we can study them on the lattice very efficiently. All right, so if you expand this model, so I'm sorry this is a little messed up, but the hopping parameters you would get for these fermions is just basically sinh k eta ij. So eta ij are some phases, and I'm going to choose the phases to get the standard staggered fermion prescription, so that I put pi flux on each plaquette. And I get Dirac fermions. So I'm going to work on a square lattice. And I know now one thing about this model is that if I make kappa very, very small, it'll have a semi-metallic phase. Okay, so, and the argument is that, when kappa is very, very small, the 4th, 6th, 8th order operators become irrelevant at the fixed point, which is described by the linear dispersion, right? This is true in 2 + 1 dimension. Okay, so I know that if kappa is very small, I have a semi-metal phase. And now the question is what happens when kappa is large, and what is the nature of the phase transition? And these are interesting questions. Okay, so kappa is my tuning parameter. It turns out for some historical reasons, I'm going to work in terms of another parameter, which is 2 tanh kappa divided by 2. It doesn't matter. This has some detail to do with the way the algorithm was constructed. Okay, so let me quickly, okay, so there was a picture over here, which for some reason is not showing up. Oh, here it is. Okay, so let me quickly tell you, something interesting about this model is that you can write this model, remember, as a sum of bond terms, where this bond is this, interesting exponential of hopping term. And this bond term is fully interacting. It's not a quadratic term. Okay, so when I sum this up, I have an interacting Hamiltonian. And so if you evaluate this in some imaginary time path integral, or you use Sandvik's stochastic series expansion, what will happen is you get configurations in which you have these bond insertions. Okay, and then what you need to evaluate is you need to evaluate the trace of this. And then you have to Monte Carlo sample different configurations of this trace. So now the beautiful thing is, because each of these bond interactions itself is an exponent, this many-body trace can be evaluated as a one-body determinant. Okay, so there's a very famous formula called the Blanken-Beckler-Sugar-Scalapino formula, which is a sort of standard thing in fermionic Monte Carlo, and maybe Farquhar mentioned it. And so basically what happens is that you can rewrite this sort of many-body trace simply as a determinant. And it's very simple to prove, this has been known for a long time, that these determinants are positive because they have 2 spin species. Okay, so they spin up and spin down, and each of them gives you a determinant, and the square of the determinant is always positive because each determinant is real. Okay, it turns out that each of the determinants is also positive, and this is something that Shailesh and Emily proved, as did Hong Yao and some other people. But that's not very important for what I'm going to say, because I'm going to work with spin. Okay, so basically now what you have to do is you have to sample all these different bond insertions. And again, Emily developed some very sophisticated methods to do this over her PhD thesis, and we're going to use those ideas here. Okay, so let's look at some data. Let me tell you basically what happens. So again, when this parameter G is very small, I argued from hand waving that this is a semi-metal. When G is very large, it becomes a massive phase. And so we want to understand what's the nature of this massive phase, right? So remember, when you add a Hubbard repulsion, when U becomes if it's repulsive, you get an antiferromagnet. If it's attractive, you get a superconductor. And now the thing is, it's neither repulsive or attractive because we don't have U. We have this other interaction. And so the question is, what happens to this massive phase? So we measured two order parameters. We measured a spin order parameter, which measures spontaneous symmetry breaking in the spin channel. And we met another order parameter, which basically is the Hubbard interaction, right? So it's n up minus a half times n down minus a half somewhere and somewhere else. And this 2-point function measures the spontaneous symmetry breaking of this Z2 Ising symmetry, the spin charge flip symmetry. Okay, so if we go into our massive phase, we find actually that both these order parameters actually go to a finite value. Okay, so if I do some freehand drawing, there's no way that they go to 0. They both go to a finite value somewhere in this massive phase. Okay, so this is the coupling constant at which this picture has been made. And so I'm going to return to the interpretation of what this means. Okay, so this spin charge flip symmetry, the symmetry that would flip you from an antiferromagnet to a superconductor, is spontaneously broken, and the system also is an antiferromagnet. Okay, so what does this all mean? We'll come to that in a second. But let me just finish all the numerical data. So this is the CS parameter as a function of L, and you can see again, it goes to a finite value in the massive phase. It goes to 0 as a power law, as you'd expect when you're in the semi-metal phase. And then there's this critical point at which you get some non-trivial power. Okay, so I think the power here is something like 2.3 or something thereabout. So that eta, which is, that this power is 1 plus eta. And I'm sorry, I didn't write it down over here. I meant to write it down, but last night I got sidetracked. It's roughly 1.3. Okay, so and now what we can do is we can take this data and we can do the standard critical collapse, and it collapses very nicely. I'm sorry, these error bars are very wide. There was some problem I was having last night getting them to work out. But so we have nice evidence that between this massive phase and massless phase, there's a nice critical point, and the critical exponents are known, and they don't match what you have for the Chiral-Heisenberg model. Okay, so the Chiral-Heisenberg model is the phase transition which has been studied intensely, numerically, and by epsilon expansions. And people have been trying to use a conformal bootstrap recently to study it. I'm not sure how I think it's partially successful, but not maybe fully done yet. Okay, so now what we'd like to do is we'd like to ask ourselves whether this phase transition is different from the Chiral-Heisenberg fixed point. Can we develop an epsilon expansion or renormalization group story for it? And yeah.
Hello. Mm-hmm. Hi. So you just showed eta. What about the other exponents? I mean, do you have the correlation length exponent? Maybe I missed that.
Yeah. My memory, and Emily's here. Maybe she knows better than me, but I think it was 0.7, roughly 0.7.
Did you have but for the Chiral-Heisenberg, you're not so much. Okay. So okay. Yeah. Okay. And the fermion anomalous dimension is the.
That's something we did not measure yet.
Okay. Thank you.
Yeah. So yeah, now I'm going to present some renormalization group field theory type arguments for why this is a separate fixed point from the usual case.
Sorry, Ribhu, could I still ask a question? If you look at the phase transition, you of course you showed that the O4 symmetry was SU2 times Z2, right?
Yeah.
So if you go into the massive phase, you do have a finite temperature phase transition, which is Ising, where you break the Z2 symmetry. Is that correct? And so the critical point?
Yeah, that's a good question, actually. We haven't really explored the finite temperature phase transition. I expect actually that we may not have a finite temperature phase transition, but I haven't thought about it carefully. And I'll explain to you why in a second.
Okay.
Because it turns out if you break the Ising symmetry, I think you also have to break one of the SU2 symmetries, which is not possible by Mermin-Wagner theorem.
Interesting. Okay, good.
Yeah, but actually, it could be that I'm wrong about this. So we should check it. And I can't remember. Maybe Emily or Hunching has some more thoughts about this. They may have thought about it more carefully. Okay, so let me show you how we set up the sort of field theory description of this. So you have this hopping problem, which say realizes a Dirac point. And now you have these two order parameters which we're interested in. One is zeta I, the sublattice factor times the spin density. So this is the antiferromagnetic order parameter, and I call that vector phi si. And then there's this charge order parameter. Okay, so the charge order parameter is basically like a superconducting order parameter and a charge density wave. Okay, so for people who work in the Hubbard model world, this is sort of a standard thing. And so if you want to describe these phases, you would use this kind of mean field theory, right? This is sort of in the mean field how you would imagine an antiferromagnet or superconductor. Okay, but now remember that under the spin charge flip symmetry, which is usually broken in the Hubbard model, these two guys interchange, right? Because SI and CI interchange. And so if you really have this symmetry, in some sense, in some effective theory, we need to consider these couplings to be equal. Okay, and I'll talk about that in a second. Okay, so basically what I can do is I want to write, so I want to do RG on some, Lagrangian. So I'm going to begin with this Hamiltonian, and then I can, do the standard steps of inserting coherent states and getting, taking the continuum limit and writing a path integral. So let me do that. And when I do that, I end up with this theory. Okay, so here's the Dirac equation. And now I have a coupling between this boson, which is a 3-component boson, and it couples to MS. Okay, MS in this continuum language is just given by this operator. Okay, so psi bar now is an 8-component field. It has 4 internal components. So there's basically 2 spin. So there's a sublattice, there's a charge, and so in condensed matter we'd say there's a sublattice, there's a charge, there's a sublattice, there's a spin, and there's a valley. Okay, and that's how you get 8. This is what happens in graphene. Okay, so you have so this alpha here is the spin index. So it basically just says that this is psi bar sigma psi is your antiferromagnetic spin density, and that acts like a mass in the Dirac equation. As is this other interesting term over here, which now has both superconducting and charge density wave components to it. Okay, so now interestingly, all 3 components of this phi s act as masses in the Dirac equation, and they all actually add in quadrature, right? Because in the Hamiltonian language, they all anti-commute with each other. And the same can be said about charge, but the same cannot be said about adding both charge and spin together. Okay, so it's sort of interesting to ask. So if you just had this term over here, there's an O3 symmetry because you can always rotate amongst your spin components, and same with the charge sector. But now when you have both, the same is not true. And the question is, can you even have coexistence of these 2 order parameters? Okay, so we can figure this out by, or at least we can provide a partial answer to this question by calculating the effective potential. Okay, so basically what I want to do is now, okay, so in addition to the coupling, this is a standard Yukawa-like coupling. And now I'm going to also put some, I'm going to give the standard 5-4 theory for bosons. Okay, and so one thing I could ask myself is, suppose I just integrated out this quadratic theory of fermions, what would the effective potential for phi s and phi c be? Okay, and so there's a simple argument that you can make that the system will always choose to be either phi s or phi c, but not both. Okay, so, or at least that's what fermions would like the system to do. Okay, and one way to understand that is to actually, so remember, because you have symmetry in the spin and charge sectors, you can rotate them into the z direction. And so you have phi zs, and that couples to psi up bar psi up minus psi bar down psi down. And you have phi charge z, which couples to psi bar up plus psi down psi down. Okay, so you see that the up electrons couple to phi plus, which is phi zs plus phi zc, and the down electrons coupled to phi minus, okay, which is phi z c minus phi zs. When you integrate them out, you get identical effective potentials for phi plus and phi minus. Okay, so when the system, and because they're identical potentials, they'll always condense the same magnitude. And so if you reconstruct phi zs and phi zc from phi plus and phi minus, you'll always have that one of them will be zero and the other will be finite. Okay, so this is a simple physical argument which explains why the system actually doesn't like having both spin and charge condensates and will naturally want to pick one or the other. Okay, and picking one or the other breaks the Z2 symmetries. So sorry, there was a question.
Yeah, I didn't understand the argument. So are you saying that the potential is symmetric with the interchange of phi plus and phi minus? Is that the?
Yeah, I mean, it's also it's symmetric under the interchange of phi z s and phi z c. But what I'm saying is, the potential sort of becomes a sum of a potential of phi plus and phi minus, and those two potentials are identical. So when they develop minima, they both will develop minima together. And so, this is the potential for phi plus, and this is the potential for phi minus. And so now spontaneously, say this picks, you go into this state. So if you go into this state, then, if I reconstruct, I'll find that, one of phi zs is 0 and one of phi zc is non-zero. So there are 4 different things that you can do, right? You can have, you can be here and here, you can be here and here. And as you do those 4 things, you'll find that either phi s is 0 and phi c is positive or negative, or phi c is 0 and phi s is positive or negative. Okay. And actually, you can compute the effective potential. And here is actually a picture of the effect. So you can compute the fermion determinant and just evaluate what it is. And as we expect, basically, the minima of this potential, lie in situations where one of these order parameters is 0 and the other is either positive or negative, and vice versa. Okay, and so we interpret this as being consistent with what we found numerically, right? So so basically, this was related to Farquhar's question, is what happens is when you break the Ising symmetry, then either S or C has to condense. So an interesting question, which I'm not sure whether it's possible, is can you break the Ising symmetry without spin or charge condensing? And I think that was Farquhar's question. The question is, can it exist at a finite temperature? And I think that's actually a very good question, which we should have thought about. And maybe we discussed, but my memory is becoming worse and worse, so I can't remember. Okay, so basically what we see is that, the Ising symmetry and the spin symmetry is broken. And so now this effective potential is an interpretation.
Ribhu, I think, so Johannes Hoffmann did some of these calculations. These are unpublished, right? So I have nothing to say. But I think that he did some of these calculations for similar questions for O4 universality classes. And what he measured was the fermion parity, right? And the fermion parity showed an Ising type. Well, you could interpret the data, which was a bit noisy, but you could interpret the data as a finite temperature Ising transition. And that would exactly mean that you have a finite temperature Ising transition, and then so at a finite temperature, the system somehow spontaneously chooses if it wants to go to the CDW or if it wants to go into the SCW phase.
I see.
So I think you should. I mean, you guys have. I mean, I think it would be worth checking, right, for that.
Yeah, absolutely.
Yeah. I remember that he had the data, but I'm older than you are, and so, I don't know anymore. But maybe Emily can ask Johannes, so that's fine. Okay,
good. So thanks a lot for suggesting that. And again, I wanted to send you or anybody else the draft of the paper before we publish it, because I'm sure there are other things that we also don't know about, and so it'll be great to get your input. Thank you. All right. So
sort of along those lines, I think. Does this has the O4 symmetry? Is that right?
Yeah, I mean the model has O4 symmetry, but it's being spontaneously broken in a certain way in this sort of massive phase.
Can you explain this business about the C and the S and the Z2, like this order parameter in O4 covariant language? Is that easy to understand, or?
Yeah, I think Hunching, my collaborator, is an expert on this, but my understanding is the Z2 symmetry is the improper transformation, the difference between SO4 and O4. So the Z2 transformation is the one that's like, I don't know, one. I mean, there's many ways to define it, but maybe -1, 1, 1, 1. It's the element of, my math is very weak, as most people who know me know. But I think that's what it is. It's -1, 1, 1, 1.
Okay.
1.
The phi C form like an O4 vector or something like
no. I think that my collaborator Hunching, who's a brilliant young guy who's looking for a postdoc too, is on this Zoom call. So maybe I really encourage Emily Hunching and you guys to answer some of these questions, which are I may not know the answer to. Yeah, go ahead.
Yeah. So I think one way to understand the O4 symmetry is to write the fermion in the Majorana language. And the O4 symmetry is like a particle hole symmetry on one layer. It will flip one of the Majorana component. And it lacks -1, 1, 1, 1 in that space.
See.
Yeah.
I see. Okay, thank you. I think that helps. Thanks.
Can I also make a question on your slide? Can you go back?
Yeah.
Oh no, one more then. No, then it was
going back.
The one with the potential. The slide, the picture with the wells. Where was that? Oh, here again. So these. So my reading of this is that you always have an SO3 symmetry, right? One of the order parameters is 0 in the vacua.
Yeah.
So could I
you could, yeah. Mm-hmm.
SO4 symmetry breaking pattern where the order parameter of SO4 gets a VEV and then variant under SO3? Is that the statement?
But the effective order has the wrong dimension to be a vector.
What do you
6 components.
No, but these are two SO3s. They somehow overlap. That's my understanding.
It's more like the self-dual and anti-self-dual embedding of two SU2s into SO4.
Right. But the model anyway has an SO4 symmetry. So I would expect on generic grounds that, once that gets a VEV, that I still have an SO3 symmetry.
But you can do that with a vector, or you could do that with a self-dual or anti-self-dual.
I guess you could, but what he's showing seems to always have an SO3 symmetry.
So I realize I'm not sure this discussion is picked up on the microphone. Maybe we should let Ribhu continue and then we can resume this afterwards. Maybe.
No. I'm just delighted that you guys are discussing this. It's warming my heart here. Okay, but let me go through this because I also want to make sure that people are not stuck on this call forever. But I'd love to discuss this with you, and I'd like to introduce you guys to Hunching too, who's kind of expert in all these things. Okay, so that's our interpretation, and now what I wanted to do was study. So basically, what we can do is take this combined Yukawa, boson model and do a one-loop calculation in the epsilon expansion. So you have 5 nonlinearities: GS, GC, lambda S, lambda C, and lambda SC. And they all become marginal in 4 dimensions. And so you can do an epsilon expansion. And I mean, for those of you who are listening who, so Hunching did this using dimensional regularization, and I did it by some momentum shell method. And after he pointed out a few mistakes in my calculation, it turns out that they agree perfectly. So we're very confident in these results. And so here's the flow equation. Okay, so these are the Yukawa couplings, GS and GC. Okay, so now, sorry. So what happened there? Yeah, so let me just say one thing that's important over here is that, so when you study this theory over here, at least the way it's written down, it always has these 2 SU2 symmetries. But in order to implement the Z2 symmetry, you have to require that the spin and charge couplings are the same. Okay, so there are these spin and charge couplings. And so when you write down the Landau theory, you can have a phi s squared times phi c squared, which is a self-interaction of bosons between spin and charge. And it doesn't matter what this guy is, but if you want spin charge symmetry, you require these two to be equal and these two to be equal. Okay, so when I show you flows, I'm going to show you some flows which don't respect that symmetry and some that do. So for example, when I show you a flow like this is GS and GC, and so the symmetric region, which in some sense the special model that we oops, I didn't mean to do that we have introduced lies along the diagonal axis here. Okay, because along this diagonal axis, GS and GC are not equal. So what you see now is that there's some, there's a Gaussian fixed point, which is completely unsafe. So by the way, these flows are for the massless theory. Okay, so when you think about critical phenomena, there's the boson mass, which is always relevant because in 4 dimensions is relevant and remains relevant in 4 minus epsilon. Or there's a direction associated with it, which is relevant. So basically, if you want to have a critical point, which is tuned by just one parameter, it has to be stable in this RG flow. So all RG flows have to flow back. So now what you recognize over here is that these fixed points are the standard Chiral-Heisenberg fixed points. Okay, so there's one basically that you'd get in the repulsive Hubbard model, and there's exactly the same one that you'd get in the attractive Hubbard model. But the interesting thing now is that this new fixed point here, which happens when GS equals GC. So if you're in the spin charge symmetric regime, you'll never reach the Chiral-Heisenberg model, right? Because the Chiral-Heisenberg model requires you to not have spin charge symmetry, requires you to have one of these couplings 0. So if they're equal, GS and GC, you can't go to the Chiral-Heisenberg model, but you can go to this new fixed point. And in this world in which the symmetry is implemented, this fixed point is stable because all flows go back into this fixed point. So notice that if you break it even slightly, it's unstable, and then you'll flow back into the standard Chiral-Heisenberg fixed point. Okay, so if you look at these beta functions, you'll notice that the beta functions for G decouple from the beta functions. In a sense, lambda doesn't appear in the beta functions for G, so you can study the fixed points of G separately. And now what we can do is we can take the fixed point values of G and ask, whether there's stable fixed points in lambda, which is a requisite to have a continuous transition. And so here is a flow in the lambda space. So there's lots of coupling, so the flow looks a little bit messy, but this is when lambda S equals lambda C. So this is completely in the symmetric space. And you notice there's just one fixed point. There's just one fixed point over here, which is this. So this is with GS and GC evaluated. I'm sorry. Clear all drawings. Okay. So this is with so this is with GS equals GC equals GS comma C star, right? So I'm evaluating it, I'm evaluating it at this GS GC value. Yeah, so you have this nice fixed point, which is stable under all directions of flow. Okay. And so that proves, at least in this epsilon expansion, that there's a new fixed point which is different from the Chiral-Heisenberg fixed point, which is spin charge symmetric. And there are many fixed points, but there's only one which satisfies all the properties we need. It has the right number of relevant directions. Okay. So that's the end of this section. I just want to say that the spin charge flip symmetry, which is sort of a fundamental property of the lattice model. I mean, technically, it's also there in it is there in the continuum Dirac equation, right? So it's also a property of the continuum Dirac equation, and it affects the kind of phases you get at strong coupling. And we find that there's a new critical point in which both superconductivity and antiferromagnetism are simultaneously quantum critical. Okay, so this is something that people have been interested in a long time in condensed matter, for critical points where there's both superconductivity and antiferromagnetism. And this is, I think, the first example of something which is very controlled. You can study in the epsilon expansion, you can study on the lattice, by first principles. And so we're very excited about that. And I think an exciting question for people who are interested in bootstrap, and people have been trying to bootstrap these kind of critical points with Dirac fermions. The question is whether you can build this Z2 spin charge flip symmetry into the bootstrap. Does it make it easier? I don't know. I'm sure something that experts could contribute to. Another question which we don't completely know the answer to is how does the spin charge flip symmetry affect other critical points? Okay, so I mean, this is one critical point, but now you can have like, I don't know, the deconfined critical point, various other things. And the question is how, whether the symmetry plays any role in those phase transitions. Okay, so that's what I have about this. And I have something else that I wanted to, I'm happy to take questions, or I mean, we can finish the discussion that was started, or talk about something else. I don't know, Tin, what is the plan?
Well, I don't know. I gave you full autonomy, but no, we can take a break. But would you mind if I ask a question?
Yeah, please. Of course, I'd love that.
So, I mean, you started studying these interactions which preserve SO4 symmetry. That's my understanding, right? You wanted to, but I'm just curious.
Well, I think technically, I mean, I shouldn't be correcting anybody else's group theory, but I think it's O4 because that Z2 is the SO4 is part of the spin and charge SU2s, and then this is that extra Z2.
O4, that's fine. My question is, what made you motivated with this? Is there some system that you find interesting, or you just wanted to explore more models which weren't explored before, or were you suspecting that there's a critical point?
Yeah, I mean, I think to be fair, I think the thing that got us, so I wish I could say, luckily this is not a hardcore condensed matter audience, because if you say that your inspiration was anything apart from a specific experiment, then they think that you're crazy. So I don't have to apologize for that. But I think that our motivation actually was, Shailesh and Emily's beautiful work on these models. And really the thing that they did was they studied it with just one spin initially. Okay, so with one spin, it turns out that this is an interesting fact, and I'm not sure if they were the first, or there was another group whose name I'm forgetting, but a few people may have realized at the same time that, the TV, so if you just take a single spin species and, you have a hopping and a repulsion between neighbors, it turns out that this exponential form is an exact representation. I mean, so these two are exactly equal. So Lai Wang, yeah, that's the person I should remember, and Matthias Stroyer. I think that they may have been the first to realize that this exponential form is the same as the TV model. So of course, from the TV model, you may not think of this generalization, but from the exponential form, it seems natural to then consider more and more spin species. And then we were kind of interested in this idea that there's a symmetry which is present in the lattice, which we can preserve in an interacting model. And I think maybe initially the motivation was that this could be a way to realize the chiral Heisenberg phase transition and study it and contribute to, what Farquhar and many other people are doing. But then it turned out that it ended up being something new when we analyzed this model. And so we got excited by it. But yeah, I think that in condensed matter world, there would be a complaint that the symmetry is present on the lattice, but it's not physical in the sense that it doesn't, it may be hard to find a way. I mean, but so often sometimes what was happened often in the history of condensed matter is people studied some model for some abstract reasons, and then 20 years later, for some very different reasons, it comes up in an experiment. That happens again and again. It's happened actually many times. And I guess I shouldn't have to say that in front of all you guys, because you're not going to hold me to that standard. Yeah. So I think that's roughly how we got involved in this model and why we think it's interesting.
Ribhu, I think that if I may comment on this, the symmetry is not so. If you take any type of electron phonon model, and you put an SSH basically, so you couple the phonon to the bond, right? Yeah. Then the symmetry is there, right? At half filling.
That's true.
On a bipartite lattice. So it's more than you'll stumble over a lot of models in my experience where you really have this O4 symmetry. So it's not so. Yeah. So I think it's not so special. Well, it is special, but it's not so special somehow.
Yeah, I mean, so the question is whether it whether it corresponds to anything that exists in nature from the point of view of condensed matter. But I agree with you that it's a very ubiquitous property of models because it exists in the free hopping model. So if you had phone-on coupling in the SSH style, it's also present in that model. Thanks. Yeah, that's a good point.
Hi, can I ask a question?
Yeah, please. Yeah.
Hi, Ribhu. Nice talk. So I have a very naive question. So, on the last slide, you mentioned that you have simultaneous critical superconductivity and antiferromagnetism. Is that built in microscopically when you put in this symmetry, or is that some non-trivial thing?
No, I think it's not. So one thing that we were not able to show is. So I mean, the relation between superconductivity and antiferromagnetism is through the Z2 symmetry, because under the Z2 symmetry, antiferromagnetism does become superconductor. So in some sense, we did put it in.
Right.
So we did enforce it, and it would be nice if it could be an emergent property.
Yeah, exactly. Yeah, I guess that's what people have been, interested in, the emergence of that, right?
Yeah. No, I think that, and again, it goes back, I think, to the question that Tin asked, is that this symmetry by itself is not natural. So it would be nice if it could emerge somehow instead of being, so we're implementing it on the lattice, right? And so that's an interesting question. And the question is whether we can have it emerge. So when I go back to those renormalization group flows, whether you could flow to it even if you didn't originate in a symmetric world. Right. And I think that's a very interesting question. And again, it may not happen in the simplest possible lattice models, but it could happen in something else. And I don't know what the answer is, but.
So I also have an even more naive question. When you put in this higher symmetry, isn't it sort of given that you have to have a different fixed point if you have a transition?
No, I mean, so let me give you an unrelated example. Like when you have the chiral Heisenberg transition, right? In the Hubbard model, there's SU2 spin and SU2 charge. Now, my understanding is the SU2 charge is an accident. It's not required to have. So, I mean, whether you break SU2 charge or not, the transition from a semi-metal to an antiferromagnet would always be the chiral Heisenberg transition. Right. So there's some symmetries which may not play a role in, I mean, whether you break them or not, may not play a role in a particular phase transition.
Right.
So,
but for the chiral, but for this, sorry to interrupt, but if you measure the charge-charge correlations of the chiral Heisenberg or the superconductor, they're just not critical.
Right, they're not critical, right? And
you're right. So they don't play anything in the critical. They don't play a role in the critical theory, right?
Yeah. So what we were wondering. Yeah. So sorry. Yeah. So to your point, what we were wondering is whether at this critical point, this Ising order parameter also becomes critical, and we didn't know that a priori. It turns out that it does. It could have been like the charge. It could have been just some spectator thing that was not important.
But I guess that's related to my other question. If simultaneous critical superconductivity and antiferromagnetism is built in, that means that the order parameter has a higher symmetry. So then it would have to be a fixed point. So then it goes back to whether that built-in thing is really guaranteeing that from the outset, right?
Yeah. Yeah, it's a good question. I mean, certainly it would be very interesting to find models in which this symmetry was not present, but somehow it would emerge at the critical point.
Right.
That is one of my follow-up questions. I mean, to answer that question is the important thing is to answer how many perturbations breaking O4 symmetry.
Absolutely, yeah.
And do you have an idea how many are relevant? How many operators are relevant? Because then you could just, pick your favorite model and change many parameters until you hit that point. It's a multi-critical point.
Yeah.
In principle, you can always get it if you're willing to fine-tune sufficiently.
Right. So I mean, that would be one route. Another route could be that there's some other symmetry which, reduces them. So I think that there might, in 4 minus epsilon at least, I think there might be 3, apart from the boson mass, there are 2 other relevant directions, right? Because there are 2 marginal operators, and you can detune both of them. So that's a lot to tune. But the question is whether there could be some other microscopics that reduces those parameters. Again, I mean, this is all very far-fetched thinking, but I think it would be interesting to think about.
I would say only if the combination of the 2 has some other symmetry, which is a bit higher,
Right.
Not O4. That's be my feeling.
I agree with that.
And then you look for microscopic symmetries which have that symmetry, and then you have to tune less. But I think it's interesting also from, I mean, is there another system with an O4 symmetry which is believed to be critical? I mean, to put this critical point.
Well, in deconfined criticality, I mean, people believe that, there could be emergent O4 or SO5, things like that. Right?
O5 there, right? Oh, or SO5.
But there's also, I don't know if it's O4 or SO4, but probably O4. If you have easy plane. I mean, Ribhu has studied that as well, right? So.
Yeah. No, I think that.
But in the end, those may be multi-critical points too. If we can ever reach them, we need to tune another parameter like.
Those theories also have 'T anomalies. And Ribhu, do you have any idea whether these models, this symmetry has a 'T anomaly? You showed some bosonic version of this, which clearly I think doesn't. But was this just a kind of Landau-Ginzburg?
Yeah. That's totally Landau-Ginzburg. Yeah.
So the microscopic model you study may actually have something.
Yeah, it's quite possible. Yeah, I'm again, something I don't know much about, but yeah, I mean, and we of course would be very excited if you guys are interested in any other aspects of these models which we haven't thought about. I mean, another thing which I again don't know much about, and certainly there are other people who know more about, is there's all these web of dualities and different critical points, and the gross novo Yukawa does appear in some of these webs, and so you could wonder how under some duality transformation, because what happens often is that some symmetry sort of plays an important role, right? Under duality transformation, it becomes non-local and becomes sort of important. And so, if this critical point, how it fits into that, and whether it sort of implies in some dual formulation that there's some new property. So sometimes turns out that there's some field theories which are hard to study, but their dual formulations can be studied on the lattice. And so I don't know we don't know yet what the dual formulations of this field theory are yet. And what role the symmetry might play in a dual formation. I mean, the important thing to us, which sounds, it's of course it's all, everyone likes their own ideas, and it's human weakness, but this Z2 symmetry looks kind of very fundamental and basic part of the hopping model. So it feels like it could be important, but I will admit to you that I'm not quite sure why it is. Like I can't point to a particular experiment or anything else, which would sort of realize it. Or a physical system, let alone experiment. So, yeah.
Just curious. I mean, Fak also studied these models with SO5 symmetry, which are Fermi. You could, in principle, break that symmetry down to O4. And is there any chance that these are same models? Or in disguise? Well, I mean,
that's a good. I mean, it's an interesting question.
So maybe I didn't think about it, but we have
You can break it down to O4.
I don't know.
Do you want to take a break, Ribhu, or do you want to just power through?
Yeah, I mean, yeah,
A couple of minutes?
yeah, we can take a couple of minutes, and I can make the second part very brief. Really, the second part, I'm not even sure is actually that interesting to. I was debating on what to talk about. I'm not sure that this audience is, but I thought that there was one aspect of it that people would be broadly interested in. I hope, I don't know, yeah. So I'm happy to do whatever. I can, yeah. We can let's just take a break. I think that'll be a good idea.
Okay. Should we say 5 minutes? Is that okay?
Yeah, that's fine. Yeah.
So we get back. Let's say that we get back 10 to 4 our local time, 10 to the hour.
Sounds good.
Ribhu,
Yeah,
do you want to continue now?
sure. Yeah.
Okay. Unfortunately, David has to leave, so we'll just wait for him. He has to catch his Wi-Fi.
Thanks for your hospitality.
Yeah.
Tim. Thanks for the talk, Ribhu.
Yeah. Thanks, David. Good to see you.
Bye, David. Okay. Nabil has just stepped out. Do you want to see if he returns? And then you can continue. Or we can maybe continue. I hear him outside, and he'll probably step in when you start. Okay. Oh, here. Okay. Yeah, you can continue.
Oh, okay. So, yeah, I mean, I was debating what to talk about, and I chose maybe something a little unconventional. And I hope that I'll try to keep it really short because I think it may not be of interest to many of you, but I hope I can interest you in it. So, so I'm going to make this really quick, okay? Because I think we're going actually already spent a lot of time on this. So, we're talking about critical points with fermions, and I was saying in the beginning that we haven't had any experimental realizations of it, we hope now with this Moray stuff we might come close to it, and we still need new ideas of how to realize an experiment. But what about quantum critical points with bosons? Okay, so you learn about all these beautiful ideas which I spoke about: renormalization group, conformal invariance, critical exponents, scaling dimensions, and all of this is intellectually very exciting, and certainly something I'm very interested in. But the question is, how much of this is ever seen in any experiment at all? So you often see that people say, oh yeah, critical points are very important in condensed matter. Like their first slide, they'll show something. But okay, actually, how many critical exponents have actually been measured in experiment? And I'll give you this bad news right away. The answer is basically almost none. Okay, it's very, very difficult experiments to do for various reasons. So it's useful to go back to experiments, I think. And so I'm going to talk a little bit about experiment. And so I hope you guys will find that interesting. I'm going to present it in a very introductory way, so it's not going to be. So I think anyone can follow it. I hope, physicists. But I think the important thing to remember is experiments can sometimes spark new ideas for how things could be beyond what we can imagine. So, if you think about thermal critical points, there's, these two pictures which you might have seen in some lectures or in books. And maybe there are a few others, but, there's a liquid gas transition. So this is a famous thing. It's called the Guggenheim plot. Actually, the scaling was predated renormalization group. So in fact, it was one of the, renormalization group in some sense was inspired by an experimental observation of scaling. So if you take various liquids and you plot their, critical, liquid gas transition, and then you scale them in a particular way, they fall onto this curve. And based on this curve, you can get one of the critical exponents of the Ising model, right? So this was a very important, first. So I mean, the mystery was that the exponent didn't fit the classical mean field theory, and then the history, and that's how we came to the renormalization group. Okay, and then another experiment which is often cited is this, the lambda transition in helium. So if you cool helium down, it becomes superfluid, and this critical exponent is the critical exponent that's been measured to the maximum accuracy. Okay, so this is the XY 3D XY alpha critical exponent. And so, but this was a very expensive experiment. You had to take liquid helium into outer space to reduce gravity and then study the critical exponent. Okay, so so these are famous examples, but these are all thermal phase transition. The question is, what happens when you study, and even these, actually the helium one is known to some accuracy. The other one is actually very inaccurate. And the theory of these critical exponents does not require conformal field theory. It just requires some very basic, renormalization group certainly is important. But I'm going to show you that there is one example that we know which actually required the whole machinery of conformal field theory and all this sort of amazing things that happened in the 80s in theoretical physics. And that's based on a material which I want to tell you a little bit about. And I'll try to make this really quick, okay? Because I'm sure that you guys are tired and paying attention to some chemistry is not going to be the most exciting thing in this state of mind. So this is something I did in collaboration with my grad student, Nishita, who basically almost did everything, the theory side, and my experimental collaborator, Peter Armitage at Johns Hopkins. And we published this in Nature Physics this year. And so I'll just be very brief. Okay, so let me just remind you about some basic facts about, the critical conformal field theory we're interested in is the most simple one, right? So when you learn about the simplest conformal field theory, you learn about the two-dimensional Ising model, or the 1+1 dimensional Ising model. Okay, so the simplest lattice realization of it is the transverse field Ising chain. And so, the two phases, you all know that. When the transverse field is small, there's a ferromagnetic phase. Transverse field is large, there's a paramagnetic phase where the spins align along the field. And then they're separated by a critical point, which has all these weird properties. So this image is from the classical representation of this critical point. You have all these fractals and interesting domains that result in interesting correlation functions, right? So all of this is well known to you guys. So now at large fields, the spins align along the fields. And so you can ask, what are the excitations? And it turns out the elementary excitations are single spin flips. Okay, so these are called, in condensed matter, we call these quasi-particle excitations, because if you think about where the energy density of the system is localized, it's localized just where this red spin is. And importantly, a single spin flip can create this localized excitation. Now, the thing that's very different is when you go into ferromagnetic state, okay, which is a small transverse field, then the spins align spontaneously in the easy axis. So they can be either up or down. And now if you ask, what is the lowest excitation of the system, it's not a spin flip, okay, because a spin flip creates two sort of domain walls. We call these domain walls, right, where the up and down spins sort of meet. And so the real lowest excitation is a single domain wall. Okay, so you have a region where all the spins are down and then they're up. Now, the interesting thing about this domain wall is that it's a very non-local excitation, right? So if you just take the all up state, you cannot create a single domain wall by a local operator. So in fact, as I showed you earlier, if you do a local operator, you always construct pairs of domain walls. Yeah, and there's a Z2, basically a Z2 conservation law for domain walls. Okay, so so all of this I think you're familiar with. And if you have a physical perturbation, so you imagine a system and you may have a neutron or light, and I'm going to show you some experiments with neutron and light. What happens is that when you try and excite the system, you always create pairs of domain walls. Okay, whereas in the simple ground state, you can create a single spin flip. Okay, so there's this amazing thing which you may have learned about, which is called the Kramers one-year duality, which says that the low temperature and high temperature phases of the Ising model are actually related to each other. And under this duality, domain wall quasi-particles become spin flip quasi-particles. Okay, so when you do this transformation, a domain wall excitation becomes a spin flip quasi-particle, and a spin flip quasi-particle becomes a domain wall quasi-particle. So as you approach the Ising model critical point, if you ask what is the energy to create a domain wall on the left side, that's exactly the same energy on the right side to create a single spin flip. Okay, and this is guaranteed by Kramers one-year duality. Okay, so I'm going to show you how lots of these interesting things now have been observed in some material. So, again, for this audience, I'm not going to go into the details of the material, but it's a complicated material. Okay, this is the unit cell. So it has all these atoms and a unit cell, and then, as in a solid, this unit cell repeats itself throughout the crystal. But effectively what happens is these blue sites over here are cobalt atoms, and they realize spin 1/2s. Okay, so roughly speaking, you have a network of spin 1/2 systems, and I'm going to argue that their interactions are somewhat reminiscent of the transverse field Ising model. Okay, so they're little moments which are like little bar magnets on the cobalt sites. Okay, and so it turns out in the crystal structure of this material, the cobalt sites basically form one-dimensional chains. And to some very good approximation, these one-dimensional chains are isolated. Okay, so, and so now what you can do is you can apply a field transverse to these moments. And, on the right is experimental data, which shows how the magnetism basically degrades. And then at some critical field, the magnetism actually goes to 0. Okay, so you have potentially something which could be like the transverse field Ising model right here. Okay, so now again, this is the detail of how the experiment is done. You send pulses of neutrons, and then you study how they scatter. And in linear response theory, basically what you measure is a time-dependent correlation function. Okay, so this is something that we're very interested in quantum field theory. So this is all in real time now. This is not imaginary time. And this is actually one of the great intellectual challenges in condensed matter, is to figure out how to compute these kind of linear responses in frequency space. It's quite difficult for Okay, so here's the experiment. This shows some experimental data as a function of momentum and energy. And what you see is that you have, some kind of dispersion. As you increase the magnetic field, the dispersion, comes down lower and lower. Let me see. Right, so you have some dispersion, it comes down lower and lower. And then, at some intermediate field, it basically crashes down to 0, and then it starts to increase again. Okay, so this looks a lot like the Ising model, right? Because remember in the Ising model, you have domain wall excitations, and their energies come down. And then on the other side, you have spin flip quasi-particles, which have finite energy. So now the interesting thing is, like we said, locally, when you have like a neutron and shines off a system, it always creates 2 domain walls, which means that a neutron, it doesn't excite it doesn't have a well-defined energy momentum relationship, right? Because you have 2 of these particles over here, and each of them can have an arbitrary energy or momentum. So when a neutron shines in such a system, you get a continuum response. Whereas at large fields, a spin flip quasi-particle can be created by a single neutron, and so you have a sharp response. Okay, so that's what's shown over here. So now, if you apply a longitudinal field, and I don't want to go into chemistry of why the longitudinal field exists, but it does appear at low temperatures. What happens is this continuum of domain walls that you have over here splits up into discrete resonances. Okay?
Ribhu?
Yeah.
I wanted to ask a quick question about the previous slide.
Please, yeah, that's great.
Which side is the domain walls excitations, and which pictures of the experiments correspond to the domain walls, to that side of the?
Yeah. So the low field is when you have the sort of Ising phase, and the high field is when you have the polarized phase.
Okay.
So it corresponds to these pictures. So this is the sort of Ising ferromagnet, and this is the high field phase where the spins are polarized along the field.
So the right-hand side looks like a dispersion relation, right? Because you're exciting one thing.
Yeah, and the left side is a dispersion relation, but then you're always creating 2 particles in this dispersion relation.
Exactly, it's a 2-particle.
Yeah, it's a 2-particle continuum. It's a 2-particle continuum. But now the interesting thing is a 2-particle continuum breaks up into discrete resonances. Okay, and so the way you can understand this is that when you apply a longitudinal field, you start paying in energy the more spins you flip against the longitudinal field. Okay, and so there's this linear confining potential that forms. And so, these resonances over here are related to the bound states of this linear Schrödinger equation. Okay, so So you have this discrete resonances over here. And so if you look at the experimental data and you look at the locations of these resonances, they actually agree really well with the linear. So this linear potential has some solutions which are like, they're called Airy functions. And if you look at the zeros of the Airy function, eigenvalues, and they agree very well with the experiment.
You for a couple of seconds. Can you say again? Airy functions, and then you.
Yeah, so you have these Airy function solutions, and so from the zeros of the Airy functions, you can get this eigenvalue spectrum. And this agrees very well with the experiment. Okay, so of course, this doesn't require conformal field theory, but this is now the question, interesting question comes, which really required conformal field theory to solve, is that, of course, this idea that you can solve just two domain walls and look at their bound state is only true when they're very dilute, right? So, I mean, if you have basically the domain walls are very far away from each other, you can think about their pairwise interaction. But the question is, what happens when the density of domain walls is very dense? Okay, and this is a very difficult problem, but it turns out that this was solved by Zamolchikov in 1987. Okay, so this is a sort of remarkable thing, is that he showed that if you take, the transverse field Ising model at the critical point, and then you apply a longitudinal field. So, of course, you all know that the 1 + 1D Ising model is completely is integrable by simple methods when you apply no longitudinal field. But when you apply a longitudinal field at the critical point in a sort of tour de force piece of work, which, I barely know the difference between SO4 and O4. So this paper is way above my pay grade, because he talks about E8, which I probably never learn until not in this lifetime. But basically, from a physics point of view, what happens is that you have, at small longitudinal fields, you have these two domain wall states. And as you increase the longitudinal transverse field and you approach the critical point, these domain wall states get very dense. And this is a difficult many-body problem. And so you require some very sophisticated methods to solve them. And so Zamolchikov showed, I think there's something about perturbed conformal field theories. So there's a conformal field theory here, and there's a perturbation, which is H parallel. And he showed that he could calculate the spectrum of excitations at the perturbed conformal field theory. Okay, and one of the important predictions he made was that the ratio of the first two excitations should be the golden mean. Okay, and so here's the experimental data which shows the two energies, and it shows that as you approach this, as you approach the conformal point or the perturbed conformal point, these two ratios approach 1 + square root of phi divided by 2. Okay, so this is not very accurate, but this, if you ask me, is probably the best evidence wherever, as far as I know, and please correct me, I'm sure somebody knows something else that I don't, but this is the only evidence, as far as I know, for something which really required conformal field theory in an experiment. So I think it's sort of fascinating and interesting. Okay, so since we're running out of time, we studied this material and we showed some other interesting things about it, and maybe I'll tell you about it. Okay, just give me 10 minutes. I'm going to give you an executive summary. Said I'm happy to talk to you afterwards. I think we should end the talk, and then you can read the paper. We have it just up here in Nature of Physics. Okay, so these are these discrete resonances when you don't have away from the critical point, which are described by Airy functions. So this experiment is slightly different. It's not neutron scattering; it's terahertz absorption. Now it turns out that when you actually do this experiment in a transverse field, it doesn't look like the Ising model at all. Okay, so it turns out that it has these discrete resonances at zero field. And first of all, why does it even have discrete? In the Ising model, the domain walls have no dispersion when you don't apply a transverse field. So in the experiment, actually, there's a very strong dispersion of domain walls even without a field. And then in the Ising model, you expect this, dispersion increases as you increase the transverse field. And then, at some point, the domain walls condense, which is the sort of critical point of the Ising model. So instead of sort of just monotonically decreasing, they do something very weird, And so our goal was to understand this and find if we can have a simple model. So the motivation for this sort of talk here was to show you that, sometimes think about experimental data, you arrive at models which you may not have written down. So it turns out this material is not described exactly by the Ising model, is described by something else. And, it turns out that's an interesting sort of statistical mechanics problem. Okay, so to sort of motivate why we were interested in this model, we have to go into the details of the crystal structure. And it turns out that this material actually has a complication, which is that there are two kinds of cobalts in a unit cell. And so the way the even pairs of cobalts and the odd pairs of cobalts interact are not the same. So even if you assume that each of them interact by an Ising interaction, it turns out that the Ising axis has to be rotated as you move along the crystal. Interesting model, which is not quite the Ising model. It's an Ising model in which, every pair of sites, there's an alternating Ising axis. So normally when you write down the Ising model, the Ising axis is identical between pairs of sites. Okay, but it turns out that if you study this crystal, there's no way to justify that. And you have to allow for the Ising axis to actually not be the same on subsequent. So it alternates because there is a lattice translation which relates alternate Ising bonds. So this bond and this bond are the same, but the even and odd bonds are different. Okay, so we call this model the twisted Kitaev chain for some historical reasons. And I maybe won't go into the details of this. But when you write this model down, it turns out that there are interesting exchanges beyond just, so there's a usual Ising exchange, but there's some weird terms which are actually allowed by the crystal symmetry that, normally as a theorist, you would not think of writing down. And there was this beautiful work by Pava, Koldea, and Parameswaran, which also arrived at the same term from slightly different considerations. So, what is the effect of these terms? It turns out that they result in some very interesting, structure for the domain wall. So it turns out domain walls actually form a band structure. And this band structure can be tuned by an external magnetic field. And, maybe again, let me just show you this. So basically, we took our model and we studied it with DMRG. And, the data over here is the experimental data. And the data over here is our theory. And it really does a beautiful job of explaining lots of the features that we didn't understand in the original model. Okay, so again, I can explain to people who are interested what these details are. But let me just end with a small piece of theoretical physics, which we were able to verify, I think, for the first time, which is a Kramers one-year duality. Okay, and so I'll be done in just a few minutes. And I thank you guys for your patience. So basically what happens is you increase the transverse field, these domain walls condense. And even though this model is not the Ising model, its symmetry breaking pattern is that of the Ising model. And so you expect close to critical point, it has universal behavior. Okay. And the transition again happens through domain wall condensation here. So remember we spoke earlier about how, Kramers one-year duality guarantees that at an Ising transition, even though the model is very different from the Ising model, close to critical point, it's universal. The gap to create domain walls is identical to the gap to create spin flip quasi-particles. So by the way, this is a picture of Kramers in 1 year. But now, interestingly, when you do experiments, you cannot create single domain walls. You always have to create pairs of domain walls. So I think maybe I skipped here. This is the experimental data. So this is some experiment that's done in Estonia with terahertz absorption. But the interesting thing is that, this is the absorption line for domain walls, and this is spin flip quasi-particles. And if we extract these lines and plot them over here, first of all, you see that these go to zero linearly. The fact that they go to zero linearly is well known from the Ising model, because remember, when you tune the transverse field, it's like a mass of Dirac fermions in 1 + 1 dimension, right? And the scaling dimension is exactly 1, and that 1 is exactly why these gaps go to zero linearly. But now there's something else which is interesting, which is the ratio of the gaps. So when you learn the theory of critical phenomena, the ratio of these gaps is a sort of universal amplitude ratio. And now by Kramers one-year duality, you can conclude that the ratio of these gaps has to exactly be 2. Okay, and it's 2 simply because you always create 2 domain walls, whereas over here you create 1 spin flip quasi-particle. Okay, I'm sorry this keeps happening. And so here is basically, the theoretical universal value of this amplitude ratio, and this is the value we extracted from the experimental data. Okay, so to conclude, this interesting model material, it leads to new models, and I think it's the first time that there's some very non-trivial prediction of conformal field theory that's been measured in any experiment. Okay, I could be wrong, or there's maybe other experiments I don't know about, but certainly in condensed matter material science, I'm pretty confident about that. And it's the first time that we've actually observed the Kramers-Warnier duality or some important feature of it in experiment. Okay, so that was the lightning quick 20-minute overview of that. And thanks so much, Tin, and I thank you all for patiently listening to this talk.
Thank you, Ribhu, and thank you for actually giving that second part. It was extremely interesting, actually.
Good. I'm happy.
First talk about an experiment which I was able to follow.
Oh, good. Yeah. I mean, I think that the reason that I want to talk about is I want to remind everybody that when we talk about paths to quantum field theory, experiment is still a very important aspect of how you arrive and think about. So Sohn, of course, spoke about quantum Hall effect, and I think in condensed matter that's certainly a very exciting way to arrive at quantum field theory. But the other way is through lattice models of magnets and graphene. And there's certainly many exciting things still happening, which we're trying to figure
out. Are there any questions for Ribhu?
I just wanted to say, this is the first time I've seen the golden ratio in real life in a way that made me happy. Normally, it always seems sort of mystical, like the petals of the flower are arranged in a golden ratio, but I feel like this is a really nice demonstration of the golden ratio.
No, I think it's. I mean, for us in condensed matter, this is really exciting. I mean, it's very rare that you can. So that wasn't my work. It was. I was excited to read the work measure some very non-trivial thing, and because most of the time when you have materials, you get stuck. It does something which is kind of trivial or boring or something. So and there are millions of materials. So every now and then there's just like 1 or 2. Your life is just sifting through all this experimental data, waiting for those few cases.
Yeah, we lost you for a couple of seconds, but I think we are able to.
Thanks a lot, guys, for organizing this. And I'm sorry that it wasn't in person. I'm sure that's as disappointing or much more disappointing for you than it's been for all of us. But I think it's, in the circumstances, it's run really well.
Actually, it was a lot of fun for us, and we were just discussing the other day. We were wondering whether it was as fun for everybody else, because there's still some sense of community here.
That's true. Yeah. So you guys do have a little bit of a gang together there.
A little bit of a gang. So I hope if it was a fraction of fun for our online participants as it was for us, I will deem it a success.
Yeah, no, there's still many talks which I haven't seen yet. I'm hoping so. Certainly, Farkas' talk that I haven't got to yet because I was getting up and making my own talk. But I'm not done with the conference yet. I hope that the links will be available for a few days at least too, so we can catch up.
Yeah, they should be. I mean, I will only remove them if the speakers ask me to. So you should feel free to. I mean, I don't think nobody so far asked me to remove them. So I hope that they will stay there, because I think virtually every single talk was fantastic, and I would like to thank you all of the speakers, and I think we can you join me in thanking all the speakers one more time. I really think we were extremely lucky that all of you agreed. You were basically all of our first choices, I think. There was every single person that we wanted here. There were several people who couldn't make it, but actually we wanted the workshop for 6 days, so not for 5. So we just yeah, we feel extremely lucky that all of you agreed, and I'm just amazed that really I think I learned something from every talk, and I don't think it's my first time that really every single talk I was engaged for full 2 hours, which I think says a lot about the quality of speakers. So thank you all one more time, and I think we are determined to do this again next year, hopefully in person. And you are all welcome to join us. We'll see how much funding we have. We'll hope to be able to finance as much as possible. But yeah, stay tuned. We will keep you posted in any case. So thank you all, and have a good day.
And actually, before we end, I want to say one more thing. So there are lots of organizers' names on the list, but the truth is that Tin did almost all of the work, in my opinion. So I would like everyone to thank Tin once.
Yeah.
So,
Thank you.
Yeah, thanks, Tin. It makes a big difference when someone really organizes a great workshop, man. It really helps everybody a lot.
You know, it was my pleasure. It really was fantastic. I've enjoyed it thoroughly, even in this online format, which initially sounded to me disappointing, but I think it was really as good as it could be. So unfortunately, you know, the one thing that would be great is for me to tell you, okay, let's now go move to the other room where wine and cheese awaits us. And I hope you are adjacent to such a room at the moment, and feel free to enjoy your wine and cheese. But yeah, next time, I hope. So yeah, let me at least stop the live stream because I feel a little bit emotional.
But Ribhu, for your last comment, basically, Luttinger liquids are also CFTs, right? So you claim that all the experiments on Luttinger liquids are not. I mean,
also, free photons are CFTs. If you
well,
want
I mean,